All right. Well, good morning, and I guess happy Wednesday. Here is, we'll talk about the midterm exam. I've posted this under midterm 2 topics in the module, so that will, our midterms on Monday. So we'll talk about what you can expect. So you are allowed a sheet of notes, writing on the front and back. Again, you'll submit it with your exam, so make sure your name is put on that, and then I'll send out a seating chart. Kind of, I don't know, that's how I run my exams. All right, so this is what you can expect. I've listed off several, what did I put? About 6 of these things, and I think 6 is too much for 50 minutes, so I will select somewhere between 4 and 5 of these things. I'm not going to tell you which ones, but be prepared. And so one is to calculate a numeric gradient for a neural network, and this will be kind of a manual calculation of the numeric gradient. So you've done this for the homework, where you kind of add like a small epsilon or something, I forget what I call it, but to each term in your weight matrix, and then you see how you do forward feed with it, and then you see how it affects the predictions, and how that and in turn how it affects your loss function, right? And so for this problem, I will provide you a very simple neural network with one hidden layer. So you'll have input layer, hidden layer, output layer, and I'll just have a couple nodes, no more than 3 nodes in any one particular layer or something like that, okay? So probably something around two nodes or something, just to kind of keep our calculations simple. And you'll have a very simple activation function, so you don't have to worry about the sigmoid activation function. Either we will have the identity function. The identity function is basically you don't do anything, you just leave it as is. Or the rectified linear unit, which is basically the identity function if it's positive, and then it's 0 if it's negative. Okay, so we'll keep our activation functions real simple, just because it's manual calculations, and if you have to mess around with log or e sub x, it gets annoying, right? But you will have to calculate, the loss, which is going to be the mean or the sum of squared errors. So that's going to be the difference between the actual value and what you predict, okay? And I will give you a small set of input data. So if you have, let's say our input layer is 2 nodes coming in, and I provide you 2 observations, your input matrix X will basically be 2 by 2, right? So you have 2 observations, 2 nodes, so you have a small square matrix. You'll do forward feed, okay, and I'll provide a set of weights and biases, and I will ask you to calculate the gradient of one of the matrices numerically, and you'll add an epsilon. So I'll say these are your initial weights. What will happen, estimate the gradient numerically by add a 0.1 to this term in the matrix, or add a 0.1 to this term in the matrix. When you do the gradient, okay, remember you do it 1 element at a time, okay? So if there are 3 elements in the matrix, you do it 1 at a time. Okay, so that will be one possibility. Okay, a common mistake is that students will add 0.1 to all of the terms in the matrix all at the same time, and that is not correct, right? So when you wrote it in your code, and if you got it right, if your thing matched kind of the analytic gradient, the way you did it was you added, your epsilon to the first term saw how it changed the output, okay, and changed the loss function, and then that gave you basically the partial for that first term. And then you did it again, but for the second term only, okay, only the second term, you left everything else the same. And the same kind of thing for the numeric gradient, okay. So that's the numeric gradient. Another possibility is for you to calculate the analytic gradient, okay? And then so for the analytic gradient, again, there'll be a very simple neural network with just one hidden layer. To keep things simple, in this case, the activation function will be the identity function, okay? So we won't even have the rectified linear unit just because this makes the derivative a little bit it's discontinuous at the origin. So, or I should say discontinuous at 0. So the identity function will be our activation function. The loss will be either your sum of squared error or mean squared error. Small set of input data. I'll provide initial set of weights, maybe bias matrices. Okay, so be prepared for either. And then you will calculate the gradient of one of the matrices analytically. Okay, and again, you are allowed to a sheet of notes. So I would recommend from the homework that you've turned in, you've calculated basically the terms of the analytic gradient. I would include that in your notes, just so you don't have to try to derive it yourself, because that's going to take forever. So have that there, and then you don't have to worry about the back propagation. But you will have to know, am I calculating the analytic gradient for the bias matrix, or for the first weight matrix or the second weight matrix, or things like that. So you'll have to be able to at least identify what you're working with and calculate the analytic gradient that way. Okay, so that's a possibility. Another possible problem is a maximum likelihood estimation problem, and so this will be similar to I guess the example that we had in lecture, and so I will, but obviously different. So I will give you some kind of univariate probability distribution, okay, and it will either be continuous or discrete. So you might get the PDF or the PMF, okay, and one of the parameters for this probability distribution will be unknown, and it has to be estimated from the data. So I think an example that we had in our lecture was we had a Bernoulli or binomial, okay, where the proportion p is unknown, okay, but or you could have a normal distribution where we'll hold, normal distribution has two parameters, and so we'll just have one unknown parameter. So for the normal distribution, we might just say, here, use this for your standard deviation, estimate the mean. There might be other things, other distributions that are possible. So, beta distribution has two parameters, and a shape 1 and a shape 2 parameter. I would say, just one of these things is unknown, or like a Poisson, the rate parameter is unknown, or I guess exponential, the rate parameter would be unknown. So you have different kinds of probability distributions with one unknown parameter. And I will say here is some observations, random observations drawn from that distribution. And based on that, you'll have to figure out your maximum likelihood estimate of the unknown parameter based on the observed data, okay? Which, this probably echoes stuff you had to do in 100B, okay? That came last quarter, right? 100B, or at least earlier. All right, and then I'll also ask you to calculate kind of the related Fisher information. And the way you'll calculate the Fisher information is it's the negative expected value of the second derivative of the log likelihood with respect to the parameter. So you'll calculate the log likelihood, take the second derivative with respect to the parameter and then get the negative expected value. But the expected value is calculated with in terms of the random variable, okay, not the parameter there. Okay, so that's a problem there. We'll have a Bayes classifier, and this Bayes classifier will be, so one possibility, so there's two potential Bayes classifier problems. One Bayes classifier problem will be based on the Bernoulli or binomial distribution, and the other Bayes classifier could be based on the normal distribution. So I'll probably just include one of these, but be prepared for either of them. And so if it's the Bernoulli or binomial, it'll be similar to getting the bags of marbles drawn from the factories. Okay, so that was the example that we saw on Monday. And so we'll say, the data that you have is a mixture of kind of, these Bernoulli or binomial observations drawn from different possible classes. Classes being, in our example was factories, and in the example that you have, if you had a test problem, it'll be something else, but you'll have these different classes. Each class will have a different probability of success. So for the marbles, it was different proportions of red marbles, and the summary information of the training data will include basically the counts and the MLE estimates of each of these things, and then you use the Bayes classifier to estimate the probability of the classes for a test case. Okay. And a similar problem, Bayes classifier for the normal distribution. We saw kind of a first example for a multivariate normal distribution on Monday as well. This one would be like a univariate, just to kind of keep things simple, just because the multivariate normal, the density function is too complicated to do by hand. It's not too complicated, but it's annoying to do by hand. So we'll just keep it as a univariate Gaussian. Okay, so you'll definitely still need a calculator because the univariate Gaussian uses e to the something, and you won't be able to do that without a calculator. So so the data will come from a mixture of a few possible classes. So it'll be a classic univariate normal distribution mixture would be like the heights of men are normally distributed with this mean, and the heights of women are normally distributed with a different mean. And if you observe somebody with this height, based only on their height, what is, if you had to give a probabilistic classification for gender or something like that, how would you do it? So that is just, it'd be something kind of like that, but different. And so, each class is a univariate Gaussian with some mean and some standard deviation. Okay. And I will provide you the estimates, MLE estimates of the mean and standard deviation. I'll also provide the PDF of the normal distribution. It's probably not a bad idea to have it in your notes, but I will provide it just to make sure, because if you don't have this, then you can't do the problem at all. So I will make sure this is in the exam, and then you'll use the Bayes classifier to do that. Okay. And then some conceptual questions, and this will cover from lecture 3-2, introducing neural networks, up to today's lecture, which is the naive Bayes classifier, which is titled lecture 6-3. But it's really week 6 Wednesday, but it'll be up to today's lecture. Okay. And that's that. Any questions? Okay. All right. Well, let's go ahead and take a look. So yeah, as far as like naive Bayes classifier, I don't have any kind of like direct calculation-based problems based on the naive Bayes classifier, but we'll talk about the naive Bayes classifier today, and I would say it's fair for me to ask a conceptual question based on the naive Bayes classifier. Okay, to pull up. I'll do this. All right. Okay. So let's take a look at our lecture for today. And so we left off talking about the Bayes classifier, and we said we use Bayes' rule to do our calculations for the Bayes classifier. And the goal is to get what is the probability that an observation belongs to a certain class given the given the values, the values of your features and your x that are coming in all of the training data, and it is going to be equal to, using Bayes' rule, we're going to do the likelihood times the prior, and then we divide by the marginal. Okay, the likelihood is basically what is the probability of getting these particular x values if the observation belonged to a particular class, and you consider all of the different possible classes. And then the prior distribution is if you didn't see the values of x, and we just asked, hey, what is the probability that something even belongs to a certain class? That's the prior, okay? And we multiply these two together to get our numerator. The denominator, on the other hand, is simply there to make sure that the numerator is the sum of the denominators, so that when you do your calculations, it's there to make sure that all of the probabilities sum to 1, okay? We ran this example where our data is a mixture coming from 3 multivariate normal distributions. And, excuse me, let me type this in. Okay, 3 multivariate normal distributions. Class A is centered at 2, 3 and has this sigma matrix. Class B is centered at 0, 0 and has this sigma matrix. And class C is centered at 2, negative 2 and has this sigma matrix, okay? And so these are our generated data points. And these ellipses here represent the distributions that were used to generate our data, okay? But if, again, we don't know the exact distributions that were used to generate our data, we have to estimate them, okay? And we estimate them just by getting maximum likelihood estimates of our data, and we just calculate the means of our observations and the variance of our observations just using these internal functions here. And so these are our estimated distributions. And so we could see, especially if you look at, say, the blue dots, you could see these ellipses are centered at the blue dots directly, and there's just a tiny bit of like negative covariance here, okay, compared to this was the distribution used to generate our blue dots, and we could see our generated dots aren't exactly centered at the actual values here, okay? So it's kind of, I guess the idea here is imagine this being like an archery target, and then you tell somebody to shoot arrows at the archery target, and they did their best, and this is kind of what the target looks like. And then on the and this over here is, let's say you're on the opposite side of the archery target, so you just see the holes coming in through the board, and then someone says, okay, based on the holes coming in through the board, guess where the center of the archery target is. And you would guess that the center is going to be right here, which is just ever so slightly different from where the actual center is, okay? And that's basically what we're doing for all of these things. So we said, okay, we generated our data from here. It comes out like this based on what the dots that we see, try to estimate where the center is, and that's what we've done here. And so they're similar, but they're not exactly the same. And so this is here we've plotted both what the actual kind of archery target was and where our guess for where the center of the archery target is, and similar, not exactly the same. Okay, but anyway, we said, hey, if we put in a test case right here, what class do we think it belongs to? And just by looking at it, we'd say, yeah, for sure that's going to be class B. That's got to be a blue dot. All right, And we will go through the calculations and we will say, yeah, indeed, it is Class B. All right, before I forget, let me give you your first view quiz answer. What is today? The 7th of May. Okay, first answer is B. B as in bear. B. Okay, so again, we're going to calculate this by doing the likelihood times the prior divided by the marginal. Our likelihood calculations are based off of our estimated things because we don't know the actual generating distribution. I guess if you did somehow know the actual generating distribution, you should use that, okay? But in most real-life situations, we don't know the generating distribution, so we just have to use our best guess for that, and our best guess is based on whatever we've estimated here. Okay, so our likelihood, we can plug in our estimated x bar and our estimated variance matrix. Okay, and I could use the actual normal multivariate normal PDF, which is this complicated thing, and I can do 1 over 2 pi to the square root of 2 over 2 d over 2 times the determinant of the variance raised to the 1/2 times e to the negative 1/2 times x nu minus the mean transpose times the inverse of the variance times x minus the mu, okay? Or x minus mean. And we get this number. Now this is kind of a pain to type in, thankfully, but my number is 0.000879. Thankfully, in R, we can just use density of the multivariate normal, and it does the same calculation for us. I say, hey, this is my observed value. My observed value is at 0, 0. My estimated mean is, at some location close to that, and my variance is this, and I get the same value, 0.000879. And I want to calculate these likelihood numbers for all three classes. Okay, I want to say, hey, what is the likelihood that it comes from Class A, which I'm estimating to be centered around 2 point something and 3 point something, or I think it's like 2.2 and 2.8 or something. Okay, what's the likelihood that it comes from Class B if it's centered at another location, and that has a higher likelihood, which makes sense. Okay, this one has the highest likelihood of our things. And then what's the likelihood it came from the green distribution, okay, Class C, and that one has the lowest likelihood because, which also makes sense because looking at this, it is quite far away from even this is our 95th percentile line, this outer edge here, and it's quite far away from that. So that one has the lowest likelihoods. We would do our likelihood times our prior probability, sum the numerator across all of the things, and divide by our to get our marginal, and then we'll divide by our marginal to get our things. Now in our case, the prior probability is prior to looking at our data, okay, what is the probability that a test case belongs to a given Class C, whatever it is, before you know anything else about it, okay? And so we would use the proportion of observations that belong to Class C. Now, in our sample of data, I have 30 observations from red, 30 observations from blue, 30 observations from green. So right now, my prior probabilities are just going to be 1/3 for each of these things. Now, you might have in a different scenario, you might not have balanced classes, and you might say like, hey, it's much more likely to be red than it is to be blue or green because whatever, reasons X, Y, Z. And that gets factored into the prior. But here I'm just going to say prior of A is the same as prior of B, which is the same as prior of C, and they're all going to be equal to 1/3. Now, because of that, because they're all equal, they'll all cancel out. And so in this particular case, because everything is balanced, it's not necessary to include it, but just for good practice, we'll include it. And so the marginal probability will be found by taking the numerator, which is the likelihood times the prior, and we add them up across all of the different possible classes. So I'm going to do likelihood times prior for class A plus likelihood times prior for class B plus the likelihood times the prior for class C. Okay, and in our case, because prior A, prior B, and prior C are all 1/3, we could just factor it all out and be like 1/3 times likelihood of A plus B plus C. But again, that's not always going to be the case, but in this particular situation, it is. Okay, and then we get our posterior by doing the likelihood times the prior divided by the marginal. So now that I've done the likelihood times the prior divided by the marginal, my results end up being this. I get 0.005, basically 0.995, and then 9 times 10 to the negative 5. So basically, this is like 1 in 10,000. I've got around 1 in 2,000. 1 in 2,000 chance of being from class A. Basically, a 99.5% chance that it's from class B, and like a 1 in 10,000 chance that it's from class C. So these are our probabilities, and that aligns with exactly what we would guess and intuit, that class B, the blue dots, has the highest probability for 0, 0. Okay, and so this is the Bayes classifier, in that we say, hey, what is the likelihood that this distribution would generate the 0.00, okay? And pretty high likelihood, okay? What's the likelihood that this distribution centered at the red dots would generate the 0.00? And we say, well, it's not very likely. It's not impossible. It is, we do sometimes get dots outside of the kind of the last ring, right? So it is possible to generate a dot outside the last ring. It is possible to generate a dot out here, but much less likely. Okay, how? And then what's the likelihood that this dot came from this green distribution? Again, it's possible to generate a dot outside of the last ring. This one's pretty far away from the last ring, so we don't like to use the word impossible, but this has a very low likelihood, low probability of generating a dot out here. And so, when you do the relative kind of likelihoods, okay, it says, yeah, you know what? Comparing the likelihood that it came from the red versus the likelihood that it came from the blue versus the likelihood it came from the green, we're going to give it a 99.5% probability it came from blue. And that makes sense, okay? All right, so here is just another example. This one, we're going to put a dot at 6, 2. Here's our test case here. All right, so if you had to guess, put these in order. Which one is the most likely, what's the next most likely, and what's the least likely? What order would you put this in? Which one's the most likely? Red, okay? Because this one is still inside kind of our last ellipse here. So this data point, first of all, is just unlikely, much less likely than any of these other ones. So like when we do like this one over here, just because it's like kind of way out there. So when you calculate your marginal probability, the marginal probability is, hey, what's the likelihood or what's the probability of getting this data point regardless of class? This one has a much lower marginal probability, okay? But if we do have this, which class do we think it came from, right? So we're going to say, yeah, most likely it came from red, because as far as the different ellipses go, this one is at least still inside the 95th percentile boundary, okay? All right, so after red, what is the second most likely? Green, because if you look at the 95th percentile boundary, you say, okay, well, it's a little bit outside of that, or it's it's decently outside of that, but it is feasible for green to generate this point. And then could it have come from blue? This is like I don't know. It's like if 95th percentile is around 2 standard deviations away from the center, this looks like it's 4, 5 standard deviations away from the center. So it seems really unlikely that it's going to be coming from blue, right? Generating something 5 standard deviations away is like on the order of, I don't know, 1 in like 200,000-ish, okay? So anyway, I guess even lower than that. So we ask, okay, what is the likelihood it came from A, the likelihood it came from B, the likelihood it came from C? We do calculate those likelihoods using the density of the multivariate normal, and we use, the mean of A and the variance of A and mean of B and variance of B for each of these things. The prior, again, is going to be 1/3 for all of them. Our marginal probability is the likelihood times the prior summed up across all of the possible classes, and we have 3 possible classes. And then we get our posterior probability by doing the likelihood times the prior divided by the marginal. And so here we get around an 80%, 79.4% it came from class A. Basically 0, okay, 10 to the minus 9. So I don't want to say 0, but really, really, really tiny, 1 in a billion kind of probability. And then the likelihood that it came from C is around 20%. So around 80% class A, 20% class C, and almost 0 for class B. Okay, so class A has the highest probability. Okay, all right, what about this? Okay, so here now it's like we have a test case at 5,1, and now it seems like, okay, could be A, could be C, and we're just kind of guessing this, and it's I don't know, maybe a touch closer to the C than it is to A, but anyway, we'll do our calculation. So if I plug this in, again, my observations at 5,1, we're going to get the likelihood using the density of the multivariate normal for each of these classes, A, B, and C. So we get our likelihood of A, likelihood B, likelihood C. Our priors are 1/3 for all of these, okay? Our margin will be our likelihood times our prior for all of our classes. And when you do this, you get around 40% A and 60% C, and then, on the order of 1 in a million for class B. So class C has the highest probability here, but only by a little bit, right? 60 versus 40%. It is quite sensitive to small little changes here. And so you have that. Here's something where it's kind of close to the center of all of these things. And so, yeah, if you get a dot here, and I said, hey, do you think it came from red, blue, or green? Now this one's a little bit harder to judge, right? Because it's like, yeah, it could have been blue, it could have been green, it could have been red. And so, yeah, if we plug this in, and so this, is a bit contrived, but I said 2.53 and 0.37 is this approximate location. And you go through our calculations, and now we're getting around 30% A, 36% B, 33% C. Okay, so class B has the slightly highest probability of the 3 classes, but only by a tiny bit. And this one would be something where, yeah, it kind of, blends in, right? This one could fit in with any of these things, right? It's something like that. Okay, so in summary, we calculate our posterior probability by doing the likelihood times the prior divided by the marginal. Again, the marginal is there to ensure that all of our posterior probabilities add up to 1, and then the likelihood is, hey, what is the probability of getting our observed values if we assumed it belonged to class C? And you assume it belongs to class C by plugging in your estimated values for your mean and sigma for that particular class, class A or class B or class C there. Okay, let me go ahead and give you your second view quiz answer, which is the letter E. E as in elephant, E. Okay, I want to move on and discuss the naive Bayes classifier, okay? So the naive Bayes classifier is pretty much the same thing as the Bayes classifier, but we simplify our estimation by putting in, a bad assumption, okay? So we intentionally just kind of just ignore a certain aspect just to kind of make our life easier, right? And we do stuff like this all the time. It's kind of just like, when we draw observations from a population without replacement, technically our probabilities change with every single thing that we draw, right? Like when you start off with a deck of 52 cards, you have a 50%, you got 26 red, 26 black cards. And so your first card has a 50% chance of being red, okay? But once you draw that card, what remains in the deck is no longer 50-50. You have 25 red and 26 black cards. And so the probability of the next card that you're drawing is a little bit different, okay? But a lot of times we just say, hey, it's too much trouble to keep track of this. Let's just say it's going to be 50% red every single time. And a lot of times it's fine. And, our rule of thumb is like, don't draw over 10% of your population. And outside of drawing a deck of cards, like, if you have a big, like the student body, then you don't worry about it, okay? But technically, that's an assumption, or, it's an approximation. And here, what we're saying is that, you might have a distribution where there is covariance. Okay, so here in the multivariate normal distribution, there is covariance terms. But the covariance terms, like, we have to estimate those. And it certainly makes our calculations a lot more complicated. So what we say is, you know what? Let's just ignore all of our covariance terms. Let's just say all of our covariances are 0. Okay? If all of our covariances are 0, then that means all of our x variables, x1, x2, x3, whatever x variables we have, they're all independent of each other, okay? That's probably not the case, all right? If you think about like, other than like flipping coins, there's a lot of things where there's covariance, okay? There might not be a ton of covariance, but a lot of things there is gonna be covariance between, what happens, right? Like what, we like to assume like the memoryless property, like of the exponential distribution and stuff like that. And the truth is, in real life, there's not a ton of memoryless things, right? Like the clothing you wear tomorrow is probably going to be influenced by the clothing you wear today, because you're not going to want to wear the exact same clothes tomorrow, right? But a lot of times we just treat it like, oh, everything's independent, right? Like what I wear. But we're just going to say, hey, you know what? Let's just say covariance 0. This is going to make our life easier, okay? And so my multivariate normal PDF, okay, because we're going to assume everything is independent, simplifies to a product of univariate densities, okay? So rather than having to do the multivariate where I have covariance between x1 and x2 and covariance between x1 and x3 and x2 and x3 and so on and so forth, I just say, hey, you know what? We've got a univariate x1, a univariate x2, and a univariate x3, and the joint distribution of everything is going to be the product, okay? So when things are independent, the joint distribution is just the product of the components. And so that's what we do, all right? And that makes our life easier, okay? So if this is our multivariate normal, we have covariance, okay? In our example, the red and blue actually were independent, but as far as the green, x1 and x2 has covariance. When we estimate it using our training data, basically I'm just going to take column 1 of our observations, right? Our red observations, column 1 of the red observations, and I get the mean of column 1. And I do the same thing for the mean of column 2. And so I'm going to get x1 for A, x1 bar for B, x1 bar for C, x2 bar, so on and so forth. And I can calculate the standard deviations for column 1 and the standard deviations for column 2. And with that, I estimate my contour lines. And it's decently okay for red, decently okay for blue. it's kind of bad for green, okay? So because green has the highest covariance, and here I'm assuming there's no covariance. So it does a bad job for green because this one has a lot of covariance. But it turns out, even though it does a terrible job of estimating this green distribution because we're assuming no covariance, it turns out that as far as a classifier goes, its performance is actually okay in a lot of situations. So in a lot of situations, there is covariance, but even if you ignore the covariance, it turns out as far as classification performance goes, it's not so bad, okay? It's not, and there's, I guess, when we do machine learning stuff, we're really kind of moving away from having a model that is correct, okay? So like linear regression, I think, at least I think when they teach it, I haven't taught 101A in a long time, but when I teach, it's like, you fit the model and then you have to check to make sure your assumptions are correct. You got to make sure that you have the homogeneity of variance and stuff like that, right? And you say, oh, okay, this doesn't fit and therefore my assumptions are violated, okay? Over here with machine learning, we just say, oh yeah, I'm gonna make bad assumptions. This is a bad assumption, but you know what? If the performance is good, then it's okay, all right? We're just saying, you know what? Yeah, I know. There is covariance and I'm ignoring it and I know that's not great, but you know what? Look, when we make predictions, it's predicting okay. So therefore, I'm not going to worry too much about it. Okay, is that good or bad? I don't know, but that's what we're doing. And so here is, if we included the covariances, we have the orange lines, and we can see the purple and the orange are kind of close for the red and blue because in actuality there was no covariance for red and blue. But then for the green ones, it's quite a bit different, right? And so, hey, let's say, how well does this perform? How well is it going to predict the blue dot, okay? Or not the blue dot, this dot at 0, 0. And so we run through the thing and we calculate the likelihood times the prior divided by the marginal. This time the likelihood is easier. Like we don't have to use the multivariate normal. We can just use d norm, okay? The normal density, and it's going to be a product, okay? Normal density for x1 times the normal density for x2, okay? Normal density for x1, normal density for x2, but we use the estimates for class A, class B, and for each of these things. So there are a bunch of parameters you have to estimate still, okay? You have to estimate the mean of x1 bar for A and the mean of x1 bar for B and stuff, but there's no covariance terms that you have to estimate, okay? Now, as far as the code goes, it feels like there were more terms we have to estimate here because I have like all of these standard deviation things, but technically, if I go back over here, when I estimated my variances, okay, this is actually a 2x2 matrix, right? So we have 4 terms in here that we're estimating. So it's, I guess, 3 unique terms being estimated here, and over here, for class A, there's only 2 unique terms that we're estimating. Okay, but anyway, all to say, this is how we calculate our likelihoods. We take the product of univariate normal densities, and we multiply them together, and we add them up. We have our priors, we get our marginal, and then so we calculate our posterior probabilities, and it's close. It's not perfect. So we still say we would still classify it as class B, okay, with around a 94%. Class C has definitely wrong. It's now up to around 5%, which is wrong. But as far as estimating what class it belongs to, class B is still the highest probability. So as far as, are we going to classify this correctly? Most likely yes, okay? And so we'll plug it in there and we get it, most likely yes. All right, you know what? I'm going to save this, the document classification. We'll save that for Friday, okay? Just because it's, we're going to run out of time, and I want to give it its proper due. So we'll save that for Friday. Let me go ahead and give you your last view quizzing answer, and it is the letter D. D as in dog. D as in dog, okay? But yeah, with the naive Bayes classifier, instead of using DMV norm for the density of the multivariate normal, and we're giving, where you have to provide an estimate of the variance covariance matrix sigma, we are just doing univariate normal, D norm, and we just give it the standard deviation of our x1 and our x2, which is simpler, okay? It might not feel that way because R, typing in DMV norm is like almost as easy as just typing in D norm. But as far as the actual calculations go and the estimates go, this is simpler mathematically. Okay, so we'll wrap things up here. So have a great rest of your day. We'll see you Friday, and good luck as you start studying for your midterm.